So in order to really get at a lot of carbon reactivity, it's very important to understand carbocations. And carbocations have a very long and pretty rich chemistry and organic chemistry that goes back to like 1890 when they were very first observation of a carbocation. And so carbocations can be sufficiently stable that you can isolate them and understand them, characterize them fully. So formation of carbocation is truly an intermediate, which is what if we scroll back up to this prior thing up here, I showed you an Sn1 diagram, even though I didn't necessarily label everything on this particular diagram. But if I did, we would have said, I'm having a hard time picking a color, that these were, of course, transition states. And I had drawn right here this little well. I had set it stable, and you can identify it, and that's called an intermediate. And an intermediate carbocation is one of the diagnostic features of an Sn1 reaction. If you see an Sn1 reaction, you can be pretty well assured that there's going to be an intermediate. And in the context of sophomore organic chemistry, it's a carbocation, even though an anion can also form in the more extreme cases. But we're just going to focus on carbocations. So Sn1, think intermediate always, and consider it a carbocation. And carbocations are sufficiently important that it's going to get its own lecture. Basically, carbocations follow this observed trend where you never see carbocation formation on methyl or even primary substituents, but you start to see formation, and in fact you see really great stability of tertiary carbocations and equivalently benzylic carbocations. In fact, the very first carbocations that were observed well before we even had regular electricity were tertiary benzylic carbocations. So there is something really remarkably stable about these things, which you can see in the benzylic case. You can imagine those have some sort of resonance contributors that stabilize them. But in the tertiary one, where there's no resonance, really that's backed up by a considerable amount of hyperconjugation. All right, and so what exactly is going on? And as a review, what is hyperconjugation? Because we had discussed this idea that as things become more substituted, they become more stable. And we discussed this with radicals, and the case is essentially the same. What stabilizes carbocations, and so I'm drawing a carbocation right here, in the tertiary sense, is the bond overlap that occurs with the neighboring groups. So I can draw all these things, and I guess if I just keep drawing them, I might as well finish. But what we have are bonds that are in plane with this open orbital right here, all right? And these bonds, if you remember our Lewis structure, are actually two electrons, all right? And we can actually kind of do this for both of these. And these two electrons are negative charges, and those negative charges can sort of participate. They can help stabilize that void of charge there in the carbon. And as a consequence, your tertiary carbons, and even to some extent your secondary carbons, are stabilized by this so-called hyperconjugation. And it's just called hyperconjugation because it is an effect through space. And then you have certain things that are like this allylic carbocation. That's pretty clearly going to be stabilized through resonance. So if we were to draw the allylic system, right here, we have a positive charge here. But remember, again, this whole system is going to be Sp2 hybridized. So if we were to draw this structure right here, what we would see is, in fact, let's just move all of these a bit over. All right, and this one is purely from hyperconjugation, so we can get that there. But if we were to draw these things out, what we would have is pi systems, all right? And then we have our pi bond here, and then this is the cation. So essentially, the resonance structure means that those will jump over here, and then that will end up on that side, and so you'll have a resonance contributor that will look like this. And that'll be plus right there. And so, arguably, you can draw that, and it'll go back. So what does the actual structure of an allylic carbocation look like? I like to draw it like this, where you have this wedged bond that sort of goes all the way through here. The problem, though, of course, with this wedge bond is it doesn't really show that the resonance structures that you draw always put the carbocation on the outsides, right? So that means that the only place where you're going to have any sort of nucleophilic attack are going to be on those two carbons. As it turns out, there's never a positive charge there, so we would never see a nucleophile actually attack there. But certainly if a carbocation forms on this carbon, as it's drawn right here, there's no reason to think through resonance that that can't also attack right there. So that's something to keep in mind. Now there are, of course, other systems that are not very stable that I've drawn up here, and that's something to sort of keep as a potential trick that one might throw at you. So if you try to put a positive charge on here, all right, so a vanillic carbocation, that's actually pretty unstable. So you have an H here and an H here, and you're going to have to draw your H out here. So this is actually just going to have to be Sp hybridized. For the case of the allylic carbocation and the benzylic carbocation, both of these can be explained through resonance. And so you can imagine that you can draw resonance structures that allow you to put these electrons, these pi electrons over here, and that puts your positive charge over here, and vice versa. And so what you'll notice in the allylic system is that you will have a positive charge that is pretty much equally distributed on that carbon and that carbon, because this other resonance contributor essentially puts the positive charge over there as well. Now the benzylic position is likewise contributed or likewise stabilized with a resonance configuration or resonance structure, because you can then imagine drawing pushing this ring around, and they can draw a bunch of different resonance structures to make this happen. And you can just keep pushing those around that ring. So resonance stabilization is an important part of a carbocation. So if you want to look for what stabilizes carbocations, you should look for resonance and hyperconjugation. Now, another important component to carbocations is that it is an Sp2 hybridized system. And I had already mentioned this in some sense, alluded to it before. But one of the defining characteristics of Sp2 systems is an inversion of chirality. That if you start off with something chiral, you'll end up with something with the opposite chirality. Not so when you go through a carbocation intermediate, because like I said before, if we were to look at this system right here, and we were to sort of, let's just actually redraw it, but without all the spinach coming off of it. Copy. And we were to look at it down here and erase all this. Just actually can erase quite a bit of it because, all right. So you can see that the carbon, I actually ended up erasing it so much that it didn't really do me much good to actually copy it, did I? CH3, we'll just add these as CH3s. You can see that as I've drawn it, a nucleophile can attack from either position. So if I started off with something that was, say, chiral, and let's just move over here. Let's say I had something that was chiral, or I started out with something that was chiral. There's a carbon, and then there's an iodine, and then we've got a CH3 here, and then that's a CH2. That's coming out towards CH2, CH3, and the thing that's going back here is a hydrogen. So this is a secondary system. All right, secondary systems do indeed form. And what I ended up with is something that's totally flat. That's CH2, CH3. All right. Now the nucleophile, of course, in an Sn1 reaction, let's get that because this will go through a carbocation intermediate. And then the nucleophile all the way over here, let's make that nice and orange, has an option. It can go on this side or it can go on this side. And if you were to draw out the final products, which I can do, either placing the carbon, CH3, we'll just draw that back there. That is still in the back, except now this one has the nucleophile on top. Or carbon, H. I want to lose our H down here. Oop, let me redraw that. So this is from the top. Now I'm going to draw it coming in from the bottom. H. There we go, a nucleophile. And if you counted, so that's obviously 4. Nucleophile is going to be 1. I don't know what the nucleophile is, but it's probably going to be bigger than a carbon. And then that's going to be 2. That's going to be 3. That's going to be 2. That's going to be 3. And we can draw our little circly bits, 1, 2, 3 back. And then if we go over here, that's 1, 2, 3. So in this particular case, our clock is rotating in the sinister direction. In this particular case, our clock is rotating in the articulated direction, R. So you get no stereochemistry because there's no reason this nucleophile up here should prefer to attack from the top or the bottom. All right, that just strikes me as neat, I guess. Maybe your mileage will vary there, but Sn1 chemistry just means you lose all of your hard-earned chirality. So if you really want to make sure that you maintain your chirality, don't go through an Sn1 reaction. Because what you end up doing is forming the, and this is a review word, racemate. All right, you racemize, you scramble your chirality. And so as a consequence, you will lose your chirality if you go through an Sn1 reaction. Something that can occur in addition to what we had discussed up here with the nucleophiles and the hyperconjugation business is that carbocations can allow for things to move around. So if you have a carbocation, one of the things that can happen with carbocations is something called rearrangements. So if you have a starting material that looks something like this, and that's going to end up, you're going to move yourself into your intermediate. That's going to then put your carbocation on a secondary carbon. Now this is frustrating, of course, to this carbon right here, right? Because we'd already discussed how much carbocations are stabilized by tertiary centers. And nothing would make this system happier if it could get that stupid carbocation right here. And actually, it can. And it will. And what happens is you've got this hydrogen right here. And that hydrogen, it sees that positive charge right there, and it well, it gets little eyes, and it's, ooh, and it can just move on over, and it kind of forms this structure here, as it just sort of does a little walk. And this is our intermediate, actually, and our intermediate moves on over. And so the hydride shifts, and it puts the carbocation here. All right? And then that goes off and leads to product. This is the most common process where a hydrogen shifts over. It's possible that an entire methyl group can move over, or an ethyl group. You can undergo larger shifts in conformation. So if you were to have something that looked like this, where you have H3C, and that undergoes this, and then this, and you have a BR group here, right? And we can actually move this out of the way, so there's not a lot of ambiguity. In fact, let's just shrink it up and put it over here, and we're going to call this a hydride shift. All right, now we have this entirely different thing, and what happens is your actual carbocation that you form is that. So what happened here, all right, wasn't a hydride shift, obviously. There was a methyl shift. So this methyl group saw the formation of a primary center, and this is well, this is quite bad, right? So you have a primary carbocation, and under these circumstances, you almost always will have a shift. Methyl shifts are not as facile as hydride shifts. You don't see them as often, mostly because moving an entire methyl group is not as energetically favorable as moving the hydride. But with the methyl group right here, eyeballing that, and the likely outcome there, I shouldn't draw it like that. That's supposed to be. And it's seeing that thing going, ooh, and so it starts to form a three-membered bridge right here, and then you end up going through this sort of intermediate to form that. That is called a methyl shift. So for instance, if you were to have this reaction right here, and I were to tell you this is being done in ethanol, your final product would go through something that looks like that, and then that's your intermediate, and then you would have something there. The ethanol, obviously the oxygen is going to be the nucleophile, OTH, ethanol. All right, and then that is what you would see, and this is called a methyl shift. And the likelihood of one of these shifts happening is pretty much dictated by how much more stable can you end up making that carbocation. So if you form a carbocation on a secondary center and a tertiary center is right next to it, there is definitely a concern for a hydride shift, and you may end up with some kind of ambiguous product. Likewise, if you form a primary carbocation somehow, which again is very unfavored, most likely explanation for you even to be able to form a primary carbocation is that the methyl shift or some kind of shift is readily available to reduce the energy of the formation of that. So this is actually a relatively facile shift. So geometrically, how does this happen? And what are some of the things that govern rearrangements? And very briefly, let's just remember, we have a carbocation intermediate. That's an Sp2 hybridized carbon. And so you have to look at these structures in 3 dimensions. So let's just consider the hydride shift example. So what exactly is going on when we have a hydride shift? So in order for a hydride shift to actually happen, and this is probably a good thing to remember, is that I've not drawn the implicit hydrogen here, but there's definitely a hydrogen already there. And so what I'm going to do is just draw this structure. And that structure, not the right one, there we go. That structure, there's a thing coming out here, and that is going to be dashed away from you, and that is coming over here, and then there's a pi orbital here, all right? So we're on the same page, and that's a carbon, and that's going to have a CH3 coming out here. Actually, what's going to make this favorable is the hydride that I've drawn is going to come down in the same plane as the carbocation, right? Because remember, hyperconjugation is stabilizing this stuff. And you've got a CH3 coming out here and looks like a CH3 going out here. And we had discussed that hyperconjugation is a factor for stabilizing, right? There's 2 electrons and they're going, they're beaming electricity over there, something or other, right? Well, this is where hyperconjugation actually gets a little too carried away. It's stabilizing so much. It's stabilizing everything so much. It's like, you know what? Why don't we just move in? I don't know if our parents will approve, but who cares, right? And that's essentially what happens. Actually, if I draw this a little bit more accurately, what happens is this hydride is going to try to move over. So it forms this transition state here, and it just moves on over. It's just ta-da, right? So if you want to think of rearrangements, you can sort of think of it as like hyperconjugation's gone too far. And it's done a good job at stabilizing the formation of carbocation. It saw what it made. It liked it so much. And it was just, thank you for giving me what you've offered, but now I'm going to go in and take the rest. And that is essentially carbocation rearrangements in a nutshell. Something that is important to point out, of course, and I had somewhat discussed it in a prior lecture, is that all of these reactions are happening in some kind of solvent. So in order to really understand how things are being accelerated, it's important to put the solvent you're doing them into context. So what helps in your solvent? All right, let's consider the rate-limiting transition states of Sn1 and Sn2 chemistry, all right? So the rate-limiting transition state of an Sn1 reaction, the way that you're being taught, is always going to have some sort of carbon. And it's going to have some sort of leaving group. And that leaving group's going to try to come off, right? And I had drawn this way up here, this sort of ridiculously long bond. And what happens when you have a bond that's getting really long is basically you have a carbon that's starting to develop more and more of a carbocation character and a leaving group that's developing more and more of a negative charge, all right? And so in this particular case, the kind of solvent that's going to stabilize this, and remember, stabilizing just means that it's going to get there faster, it's lower energy, is going to be something that can minimize the energetics. Remember, you're forming a dipole, and dipoles are higher energy as they form. Nature does not want charge separation. It likes things to be stuck together, actually. But if you're going to form a dipole, why not actually just come in with acetone? All right, let's say your solvent is acetone. That's a great solvent. So this is the acetone molecule. It's a lovely solvent. It has a funny smell. It's very good at removing fingernail polish. You've probably purchased either it or its cousin, ethyl acetate. So these are both available at your supermarket as nail polish remover. But this is ethyl acetate. You can see it's got the ester here. And it doesn't make any sort of difference. What both of them have, to varying degrees, is this dipole that goes along here, and we can even draw in that that's going to be partially negative and that's going to be partially positive. And as it's already been made, what that means is that the acetone can start to align itself right here, and this is helpful, or the ethyl acetate as I'm drawing. And that means that this partial negative charge can align that other system, essentially stabilizing it. So if you have a polar solvent like this, polar solvents help stabilize Sn2 transition states. So let's write that down. Polar solvents help stabilize Sn2 transition states. That's almost always going to be true. Sn2, there is some ambiguity, of course, because chemistry is never black and white. But let's really think about what kind of transition states Sn2 stabilizes. And if we imagine that in the transition state for Sn2, so this is all Sn1. So what I'm going to do is I'm going to now shrink this down. There we go. So then I'm going to shrink that down and put it right there. So this is all Sn1. And Sn1 is cool. Sn2 is a little bit less cool. What happens in an Sn2 transition state? Well, Sn2 transition states always have something. They're that crazy five-membered carbon deuterium, what's it, right? And there's always a leaving group coming off, all right? And that's no different than over here. So you still have, as the leaving group comes off, a partial positive developing on your carbon and a partial negative. But what happens in the case of a nucleophile, right? And so in a nucleophile, it depends. If your nucleophile is something negatively charged, let's say it's ethoxide, O, and that is starting to form, that is your other side, that is coming in as a partial negative charge, right? So it is actually starting to develop it's always going to be partial negative. It's going to become less negative, but it's coming in as a negative charge. So, So the transition state, and I made that a little too long, I think. I don't think it needs to be that long. So the transition state, when your attacking group is negatively charged, looks like that, which shows no polarity whatsoever. No polarity. So that means that your transition state is not stabilized in any sort of polar solvents. If, on the other hand, your nucleophile is just a lone pair, so we say NH3, and that's a lone pair, and it's coming into, again, your carbon, that is 5-coordinate, and the departing iodine. What happens here? This is a slightly different case, right? Because the iodine is still coming off. That's still negative charge. That's still a positive charge. But what happens to ammonia, right, when it becomes protonated? Ammonias like to have 4 bonds, all right, or 3 bonds in a lone pair. In this particular case, it's giving up its lone pair to the carbon, so it's developing a partial positive charge. Essentially, in the case of, and this is how you can try to remember it if you want, the transition state of an Sn2 reaction when the nucleophile is negatively charged is not polar. The transition state of an Sn2 reaction when the nucleophile is uncharged and is just a lone pair is polar. So polarity exists. So at the end of the day, a lot of students want to know, what are we going to be tested on? And essentially, I think what you want to try to remember is SN1 reactions are pretty much more straightforward. Polar solvents are going to be helpful. SN2 reactions, that really depends on the reaction that you're going to end up going through. But if you really want to think about it critically, in order to understand how solvents affect the rate of the reaction, you have to look at the transition state. Okay? That is what I'm trying to get across to you. These are individual facts. I don't see why it would be tough for you to remember that a neutral nucleophile in an SN2 reaction is helped by a polar solvent and a charged nucleophile is not. But you can take whatever you want out of that. But these are the general rules for an SN2 reaction.